Got it. Hello. Assalamu alaikum. Today we will be discuss about our latest educational Codeforces round 153 type 2's all three problem from A to C. Before I start the discussion, might try to I think that all of you read the problem statement from your own responsibility. I will try to just show the main graphic view of the problem. So let's start the discussion. Our first problem of latest educational contest is A, not a substring. So what is the main wanted thing they wanted from us? The prerequisite of this problem is to know about the contiguous substring. I think many of them can be face a struggle. Many of them can be face a struggle to just solve this word contiguous substring. Contiguous substring is a subarray or a partition of a string. Let's assume that this is a string S. Let's assume that this is a string S. Cut a partition from L to R from this string. This part of L to R is our contiguous substring. This part from L to R is our contiguous substring. So let's start the main discussion. They give us a string S, or they give us a bracket sequence S. They give us a bracket sequence S of length n. They give us a bracket sequence S of length n. Our duty or our task is to construct another bracket sequence T whose length is twice n. Our target is to build another bracket sequence T of length twice n. So some of the condition we have to follow now. So what is the condition? This condition is in our builded bracket sequence T, there we doesn't have any contiguous substring which contain the main string or main bracket sequence S of length n. This is our main requirement. So just assume that they give us a bracket sequence like this way. They give us a bracket sequence like this way. We build another bracket sequence of length 6 like this way. This is not valid. Why not valid? Because this is our main bracket sequence given from this system. This is our builded bracket sequence T, and if we T of length twice n, if we assume that the bracket sequence, if we assume from this bracket sequence T, we find the position from 1 to 3 is present. 1 to 3 is a replicate of the main string S. 1 to 3 is the replicate of main string S. That means we have to find a replicate of a string from any partition of our builded string. So we have to build our string T in such a way that from any partition of the builded string not contain the main bracket sequence S as a given sequence. This is our main requirement. So let's solve some example. Then I think this will be more clear to you. This example, and our output is if this is possible to build up, we have to print yes, and at the next line we have to print our builded string T of length twice n. If this is not possible to build such kind of string, we will print no. So let's see an example. Let's say this example. So what will be the answer? What can be the answer of this sequence? The length of our builded string will be 8 because the initial length of the string is n. So what? How we can build this sequence? 1, 2, 3, 4. 1, 2, 3, 4. If we build our sequence as this way, then this string S cannot create any replica among our constructed string. This string S cannot build any replica among our builded string twice n. So this is our answer, yes, and this is our string. And if we see another example, first bracket. This answer is always impossible. Why this answer is always impossible? Because we have to build a regular bracket sequence of t. If our constructed string t will be regular bracket sequence always. Our constructed bracket sequence will be regular bracket sequence always. So this sequence is very common. This sequence is very common for any regular bracket sequence, because somehow our bracket sequence, regular bracket sequence will be as this way, somehow as this way. So every time this point can create any replica point among our string, among our built string t of length twice n. So if our value of n is 2 and the given string is this, so our answer is always impossible. Otherwise our answer is always possible. Why our answer is always possible? Our built answer will be as this way. Our built answer will be as this way, or as this way, as this way. Why this will be valid for us? If why this is valid for us? This is valid for us because no string or bracket sequence of length n cannot create any replicate point among this built string twice n. Why? Because if some at the first time, let's assume that we built a bracket sequence as this way at the first time, then we find a replicate point of string s among this sequence. So let's try another approach. This is this approach. Our string s it is impossible to build a replicate point between these two patterns string of these two pattern string of t. So at the first time we will build a string pattern as this way, then check that our s point is situated in this string or not. If this is situated, we will create the string as this way. We will create our string as this way. So let's jump to the code, or let's jump to the solution. At the first time we will check that if our value of n is 2 or not. If this is, and our given string is a regular bracket sequence and two length regular bracket sequence, then our answer will be always no. Otherwise our answer will be always yes. So at the first time we will create this pattern and check with a string method dot contains. This is a regular method. As I am a Java user, so I use this contains method to check a substring or pattern x is situated in the string t or not. So at the first time build this sequence and check that this sequence is sequence or pattern x or our main given string is present in this built string or not. If this is present in our constructed string, then we will create this type of pattern. We will create this type of pattern. Then this is our answer. That answer is always valid. If this main string s is not presented as a continuous sequence of the first string we will build at the first time, or our string we will build as this pattern, then we will directly print it, because string s cannot create any replicate point among this built string t. So print the s and our original string. So let's jump to the problem B. Is it recorded? Yes, this is recorded. B, fancy point. So what is the main requirement of this problem? Monocarp, somehow a person, he wants to buy total m number of coins. They use balls, but for I use coinator. This is the same factor. This is not our main observation. So he wants to purchase total m number of coins. And how many types of coins he has? He has two types of coins. One types of coin is 1 and another types of coin is k types of coins. he has infinite number of storage of one type of coin and k number of coins. And among this one number of coins, among this one number of coins, he has total a1 regular number of sequence, and infinitely many fancy number of sequence, infinitely many, let's fit it, infinitely many fancy number of sequence f. And this is same for the coins k. We have total ak number of regular coins, and infinitely many types of fancy coins. As a input, the system gives us the value of m, the value of a1, value of ak, and value of k. Our task is to find or constructed our system as this way, so that the minimum number of infinite coin we have to build. We do not need to show the what types of coin we use, how many number of times. We have to just print that how many minimum number of fancy coin we have to use. So let's solve an example, then this will be more clear. Let's pick our first example, 11, 3 and 0, 0. 11, 3 and 0, 0. So how many coin he wants to purchase? Total m number of coins, and as a value of k he has 3. He has total 0 number of regular coins, and total AK 0 number of AK coins. So for my advantage of discussion, I will try to show the main point from the reverse way, as this way. So 11, as he has not any regular bracket sequence, so he have to use all of his fancy coins. So from 11 to 11 he will go to 8, use the first 3 coins. From 8 he will go 5, and 5 to 2, 2 to 1, and 1 to 0. How many fancy coin he need to use? 1, 2, 3, 4 and 5. He need to use total 5 number of fancy coins. So main original graphic view or original situation will be goes from this right to left view, not left to right view. As initially he has not purchased any coin, or initially he has total 0 number of coins. So this 5 is our main requirement, that he need to use total 5 number of fancy coin. We need to minimize this uses of fancy number of coins. So let's solve another example, 11, 3, 20 and 20. 11, 3, 20 and 20. 11, 3, 20 and 20. Here our storage of A1 is 20 and storage of AK is 20. So uses of 11 number of one regular coins is enough to purchase the figure M. So we do not need to use any fancy number of coins, because we have enough number of regular coins. So here the total number of fancy coin we use at here is 0. Next, solve another example, 11, 3, 6 and 1. 11, 3, 6 and 1. That's very fine. This is our value of M, this is our value of K, and this is our value of A1, and this is our value of AK. So try to at the first time try to solve this pattern with the regular number of coins, then we will use fancy number of coins. So from 11 he used, at the first time he used 1 number of regular coins of A1, then he used another 1 number of coins, 9. From 9 he will go to 8. In this state we will not yet use any single number of fancy coins. We will just complete this with our storage regular coin. So 8 to 7 and 7 to 6. 7 to 6. He used total 1 2 3 4 5 5 number of one regular coins. So he can use only one number of k coins, that means 3 coins. So from 6 he can go to the 3. This state is also fill up with our storage regular coin. So now we haven't any regular coins. Now I have to use, or we have to use our stored fancy number of coins. So I use one number of fancy coins of type k, that will bring me 3 to 0, and I will be able to purchase the total amount m from here. I am able to purchase total amount m from here. So our regular sequence is 0. From 0 I use one fancy number of coins, and then use total 5 number of one types of coins, and then use one number of k types of coins. Then I need to use total one number of fancy coin at here. This is our minimized situation. So to solve this view, at the first time, what we need to do, at the first time we will try to find the remaining coin. At the first time we will try to find the remaining number of coins we have, that we need to filter this amount with our fancy storage f. We have to find the remaining number of coins after using all the regular number of coins. We need to find the number of we need to find the remaining number of coins. We need to find the I again repeat that we need to find the remaining number of coins after using all the regular number of coins. So how many one types of coin we need to use? How many one types of coin we need to use? Just numbered it from num1. So how many one types of coin we need to use? As the total bracket sequence, as the total sequence is m, this is the main amount we need to purchase. To purchase this amount, as we need to minimize the users number of users coins, so reduce the point with -1 ratio and reduce the point with by k ratio, which will be giving us the minimum result. Of course by k ratio, so we need to use maximum number of k types of fancy coins to minimize our answer. We need to use maximum number of k types of fancy coins to minimize our answer. So our value will be m. This is our main storage. This is our total k types of storage we need to fill up. K types of storage we need to fill up. So total m number of storage we have. What is our ratio? Total k, m by k. As at each step we will reduce k from here. So our total number of reducing state or reducing operation will be m by k. This is a simple mathematical form. Total number of reducing operation will be m by k. And how many number of k storage we have as a regular sequence? We can use the minimum among all. We can fill up this storage. We can fill up this amount of coin from our regular sequence. This is our total number of sequence. If we can fulfill our total storage with the using our k regular number of coins, then this is okay. If we can fill up our storage with this regular m by k sequence, then this is okay. But if we have enough storage than m by k, comparing with m by k, if we do not have enough storage of ak by comparing with m by k, then we will collect the minimum one. So as this same way, we have to count the number of one coins we need to use at here. So what is the first situation? Just considering this situation as a true. So n minus, we use total k amounts of ak coins. So k into num k, This is our one possibility. This is our one possibility. And another possibility, how many number of 1 coins we have. Total A1 number of coins we will have. So collect the minimum among all of them. So we will find that how many number of k coins we need to use as a regular bracket sequence, as a regular stored coin, and how many number of coins type 1 we need to use from our stored regular number of coins. We will find it. So how many remaining coins we will have? This I assume that this value is r. So how many remaining coins we will have? So we have total n number of storage. Just assume it m and n is equal to m. Just assume that n is equal to m. Just assume n is equal to m. So from n we will deduct the number of 1 types of coin we will use. Number of 1 types of coin we will use, and total k amounts of total ak number of coins we will total ak number of num2 coin we will use. Total ak number of num2 coins we will use. Sorry, I mean just remove it and write again. Total num2 number of k total num2 amount of k2 coins we will use. This is our remaining value. This is our remaining value. We will ensure that this remaining value, all of this amount will be fulfilled from our fancy storage. All of this amount will be fulfilled from our fancy storage. So what happened? What happened if this value is divisible by k? We will discuss at the first time that to reducing the total amount, decreasing 1 by 1 is orthogonal solution than comparing with orthogonal solution than comparing the reducing the total number of amount with the k ratio, of points. So if our value is if this remaining value is already divisible by k, that means we can fulfill this amount, total amount r, by using our stored k types of coins. So our total stored total using fancy number of coin will be r by k. Let's assume another example. How many remaining we will have after using this? So k, as we try to find the number r percentage k, so this amount will never cross the value of k. So k minus r percentage k. This is our total stored. This is our first possibility. This is our second possibility, that after using the k types of coins, how many stored coin we will have. If this stored rate will be less than our types of regular coins, or number of 1 regular coins, then what will be our solution? Then our solution will be r by k plus 1. Then our solution will be r by k plus 1. Why this solution is satisfied? Let's assume that 11. How many times we can fulfill at here, and our value of k will be 3. So from 11% 3 will be 2. If we have enough storage 3, let's assume that we have total 3 number of a1 3 number of 1 coins. So then how we can fulfill this situation? This situation will be 11 by 3 plus 1. 11 by 3 plus 1. So let's assume that what will be our solution? We will always collect the floor value from here. 3 plus 1, 4. So how 4 will come? 11, 8, 5, 2, and one and 0. The remaining remaining value is 2, and our stored sequence is by 2. So does we use this regular value directly at here? We'll pick the 11 by 3's ceiling value. So 4 plus 1. The 11 by 3 is 3 point something. So 4 plus 1 is 5. 4 plus 1 is 5. 4 plus 1 is 5. Total 5 number of coins. 3 and 2, 5. So we'll find our next situation, and observe another situation, that is the remaining fulfill with the remaining amount with both types of 1 and k coins. So in this situation our answer will be r by k, total number of uses of k coins, and total number of uses of 1 coins. Total number of uses of 1 coins. This is our answer. So between these three cases we can solve our problem. So let's assume this situation. 11 3 6 and 1. 11 3 6 and 1. Another explanation we have between this second collecting point. What is, let's assume this let's assume this consultant. How many number of coins how many number of 1 coins we will use at here? Total 5 number of 1 coins we will use at here. But how many coin we will have? How many coin we had? 6 number of coin. How many remaining number of A1 coins we have already? This is 1. This reducing sequence is come from this calculation. This reducing sequence will come from this calculation, that how many coins we will skip at here. This calculation will be this calculation will be solved from this equation. So 11 3 6 and 1. So what is our fastest storage? Let's assume what is our first possibilities? 11 3 6 and 1. So num1, at the first time calculate num1. What is our value of num1? This value of num1 is sorry, num_k. This value of num_k is 11 by 3, that we total amount we need to fill with this k, and how many storage we have? Total 1. So collect the minimum among them. So this is the minimum value is 1. We can use total 1 number of regular k coins. Let's assume number of 1 coins. So 11 minus 3 into 1, and how many we have? 6. Collect the minimum among them. So 11 minus 3 is 8 and 6 is minimum, so this value is 6. How many remaining coin we have? 11 minus 6 minus 3 into 1. So what the value we have? 11 minus 6 minus 3. 11 minus 3 minus 6, 2. If you assume this situation, or if you assume this example, we assume with this example where we use all the regular number of coins. So 11, from 11 it will at the first time go at the 10, and at the second time it will go 9, 8, 7, 6 and 5. We will use all number of A1 types of coins we have in our regular storage. So 5, from 5 we will go at this we will use 1 k types of coins. 2 remaining coin will be fulfilled, will be fancy storage. So fancy storage will be fulfilled with 2 number of coins if we use all number of stored regular types of coins. So let's calculate this. 2 is divisible by k or not? No, we cannot use any k types of coins to fulfill this situation, because 2% 3 is not equal to 0. So this situation is not fulfilled. Let's assume that how many remaining value we have. So k minus 2% is 3. 2% is 3. The storage is 1. This is less than A1, storage A1, yes, if we think that we will missing or we will skip total one types of we will missing total one types of one number of one types of one coins at here to matching with the situation where it will be divisible by k, or we can use or fulfill the remaining amount by the ratio of the k, so how many coins we have? Total remaining value r by k plus 1. What is our value of r? This is 11, this is 11 by 3 plus 1, 3 plus 1, sorry 2, sorry 2 by 3 plus 1. So in this way this can solve that how many value we need to skip from here, r by k. This will find the latest divisor of the value k between 1 to r we have. Then we will use plus 1 because we will fulfill the remaining k amounts of time or remaining amounts. We will reach initially we will reach the situation k minus 1, and we will fulfill the next amount from and reduce. This is our reducing point or reducing amount. After reducing this amount, this will reached at the position k, and then we will use total one number of k storage from total one number of 1 coins at to fulfill this storage. So 2 by 3 this will be 0 plus 1. We need to use total one number of fancy coins at here. This is our minimum sequence. Let's solve another example with this with these equations or with these three conditions: 11, 3, 20 and 20. If we see that this value of a1 is greater than or is equal to our total storage m, so we do not use any number of fancy coin at here, so our answer will be directly 0. Another possibilities we need to check at here, from here. This is total m by k. How many k number of coins we need to use if this is greater than or is equal to m, and such that m percentage k remaining values we need to use from here. This condition will be fulfilled at the same time. So m percentage k is greater than or is equal to m, then also our answer is 0. Why this answer is 0? Because we can fulfill it from our storage sequence. So let's assume that our value of m is 11, our value of m is 12, and our value of m is 12. So our value of k is 1. This is greater than or is equal to m. 12% is 1. 12%. What is 12% is 1? 12% is 1 is 12% no, sorry, 12% is 1. So this is also 12% is 1. This is also 12. Or if we divided 12 by 12 then by 1, this will be 1. So this will be greater than or is equal to 12. So in this situation we can fulfill this amount with the regular storage, from our regular storage. So our answer will be 0. So let's jump into the code. So this is our solution of the B. So at the first time we will try to find the best cases that we can fulfill our total amount or total purchase amount m with our stored regular coins. Then pick the total number of k we need and total number of 1 we need to use, and the remaining value if we use all the value of stored regular coins. So let's assume that if this amount can be able to fulfill with by using only k types of coins. This amount is able to fulfill by using only k types of coins. So our answer will be remaining need by k. Otherwise we will check that how many number of coins 1 we will skip to use at here. How many number of coins of type 1 we will skip to use at here. This amount gives us that number. We check that we can fulfill that amount with a1 or not. We can fulfill that amount with a1 or not. If this will fulfill our k value with remaining need by k plus 1 for using the latest, plus 1 for using the latest number of k coins we will use at here. Otherwise we need to fulfill this total remaining amount by using both types of coin 1 and k, both types of coin with 1 and k. So then our equation will be remaining need by k plus remaining need percentage k. This is our solution of the problem B. Is it recorded? Now I try to discuss about the problem C from this contest. This problem C was much more easier than problem B. Problem B is much also easy. This is B1 of solution. Just need to create some equation and find some points. But problems B has some little much of tricky points. But problem C is a straightforward solution. What is the solution? Alice and Bob, they are two participants who play a game and they have a chip C. And they have a permutation P. We know that what is permutation. Here all the value of 1 to k, 1 to n will be exist if the length of the sequence is n. So as example 1 2 3, this is the permutation. So which step they can do? Let's assume that this is a permutation. Let's assume that this is a permutation. Let's assume that this is a permutation P of length 5. This is a permutation P of length 5. At the first time, Alice can place this chip at any position or at any element of this permutation. At any element of this permutation. Then when Bob takes his turn, he will shift this permutation, or he will shift this chip. He will shift this chip with from the lefter element than present element and shift it on that element of this permutation, such element of this permutation when the current element is strictly greater than the newly placed value, and current position will be also greater than newly placed position j. This is our situation. So P of I will be greater than P of j, and I must be greater than j. And alternatively they takes that turn. At the first time Alice will place the chip, and next both of them take this turn after 1 by 1. So let's solve an example, then this will be more clear. 2 1 4 and 3. This is a permutation. 2 1 4 and 3. 2 1 4 and 3. So let's I think 5 for explain it more clearly. At the first time Alice will place the chip on the 5. So on the next move, at the first time Alice will place this situation and place the chip on the 5, and after that Bob will shift this chip from 5 to 3. Why he can shift at here? Because 3 is lesser than the present position I, and 3 is also smaller than present element P of I. Then Alice can again shift it from 3 to 1 or 3 to 2. Why he can shift it? Because position of 1 is smaller than the current position, and 1 is smaller than the present element 3. So this is the main sequence, or this is the main graphic. This is the main rules of this game. And what is the winning, or what is the winning strategy? the winning strategy is little more different from the regular game theories approach. In regular game theories approach, the latest move, that player will win the game which player takes the latest number of moves, or that player will be lose the game which player does not get his move. This game is this problem is little much different from that. Why? Because here that player will be win the game, that player X will be win the game who does not get his final move, here that player X will be win the game who does not get his final move, So let's assume that Alice at the first time plays the chip. Then Bob will take his turn. If Alice does not find his next position to play his move, then Alice will be win the game. If this situation will be happen at the first time, Alice will place the chip on here. Then Bob will take his turn, and then Alice is take his turn, and after that Bob does not find his position to take his turn. In that situation, Bob will win the game. This is the main strategy of our problem. This is the main winning strategy of our game. So what the solution we have? So let's solve some more example. 1 2 1 3 2 1 and 3. At the first time, we does not know any algorithm or any solution at here. What the main requirement of this problem? We need to find the total number of lucky points from this permutation. What is the lucky points? Lucky points is such kind of points. In which position, at which point if Alice will place the chip, however the strategy Bob will place, always Alice will win the game. The lucky point is such kind of points at which point Bob will if Alice will place the chip. Lucky points is such kind of point if that point Alice will place the chip at his first move, then however strategy Bob will play, always Alice will win the game. We need to count the total number of lucky points from this permutation. We do not need to show that how many points we have at here. We just need to show the total number of counting. We need to show the total number of lucky points at here. So let's solve this example 2 1 and 3. Let's assume that at the place of 2, if Alice plays this position, then Alice declared the Bob as a winner from his first move, because there is no left point of this permutation. So Bob will win the game. Bob cannot get his move. So let's assume that at the position 1 he will place his turn. If this place Alice will place his chip at his first move, then Alice will declare the Bob as a winner, because there is no smaller element. X is situated from the left side of this permutation. So what is our true observation? If there is no element that is strictly less than that current element of I from the left side or left region of this left region of this element, from 0 position to I minus 1 position, between this range, if any element that is less than I is not present at here, then that position will not be chosen by any player. The leftmost position is also not chosen by any player, because there is no left element of here. So if we place the chips from 2 and 1, then answer will not be possible. So if he place his chip from this 3, then he can win the game. Because why? Because then Bob need to place his chip or turn between these two elements. So Alice do not get his move after the third time. Alice do not get his move after the third movement of this game. So Alice will win the game. So let's solve another example. This is 2 and 1. This is 2 and 1. In this game, however the place Alice will place the cheese, he will lose the game. So total number of point is 0. This we can show from our previously solved example. So let's solve another example. 1, 2 and 3. 1, 2 and 3. 1 and 2, if he places cheese on the 2 position, 1 is not suitable for place cheese chip. This will discuss from our previous discussion. 2, if he placed a chip from 2, then Bob need to take his move at this position, so he get the leftmost position. So Bob will lose the game, because Alice second move he cannot find any move. So at the first time Alice will place the chip, then Bob takes his turn, and then Alice does not get his move. So Alice will win the game. So we will find total one number of lucky points at here. So 1, 2 and 3. 1, 2 and 3. Let's assume that Alice will place the chip at this point. Then Alice will place the chip at this point. Then Bob will shift this at here. Then Alice get his third move, and after this move Bob does not get any turn. Bob does not get any position to place his chip. So Bob will win the game. So let's solve this example. 2, 1, 4, 3. We will solve this at our previous state. So our total lucky points is 4 and 3 at here. Because if he plays chip from 4, he have to place between these 2 position, and this 2 position is not suitable. If he plays chip on this 3, then he have to place this chip between these 2 position. So what is the observation we will get from this solved example? Bob cannot get his second number of movement, because they can remove the chip from his own independence if the position is suitable according to the rules. So Bob do not need to find his second movement. Bob do not need to find the second movement if we want that Alice will win the game. Because if Bob gets his second movement, if both players are same intelligence, their intelligence level is same. So if Alice takes a move on put his chip on such a element, then Bob takes his move, and Alice can take his second move. And Bob need to take his second move. Alice can't. When our situation will be failed, when Alice can take his second move and Bob need to play his second move. Alice can take his second move and Bob need to play his second move. Bob need to play his second move. In that situation, always Bob will win the game and Alice will lose the game if their intelligence level is same. So we need to find such a position. We need to find such a position X that from this position of X there is only one smaller number Y from this number's left region that is smaller than X. We need to find such position X. So what is the prerequisite to solve this problem? This is the any balanced binary search tree. This is any balanced binary search tree like AVL tree or red black tree. This is the prerequisite to solve this problem. If you want to use the library function directly, then you can use tree set at here, as I am a Java user. Tree set at here, and in C++ you can also use the ordered set to solve this problem. So for the beginners, my suggestion is never use tree set directly. If you have not knowledge, or if you do not know about AVL tree and know details, if you know in briefly about the AVL tree and red black tree, if you do not know briefly about the red black tree or ABL tree, then you do not using the tree set is not suitable for the beginners. So if this both of them internally tree set will be implemented red black tree data structure. Here three operation we need to find. At floor, this will find the smallest value of the left region. This will find the smallest value of the left region by comparing the value x. This will find and another variable contains. This will find this will help you to find such element x is present in this list or not. So all of them take log 2 of n time. In if we implemented the binary search tree like ABL tree or red black tree manually, and if we use tree set, then also this will take the same amount of time. Also this will take the same number of time. So in both cases we will get the same complexity, but using the library function directly, JDK can be take some more memory space or some more can take some more memory space or some other region. So you can implemented this balanced binary search tree manually. So what we need to do at here to solve this problem, if we pick this example to 1, 4 and 3, we need to use tree set, and we need to find that all the value we have between 0 to I minus position, I minus 1 position, when I am stand on the position I. So all this variable is stored in all variable, and this is the variable of Alice movement, that what position Alice can take, So leftmost position is not suitable at here, so we will add it at the first time in all position, and started count from the second position. When we'll find that second position, what is our main target? Our main target is if the current number is x, and if this number have to be a lucky number, then from this number left region there have only one number y that is less than x. This situation we need to achieve. So what we need to do at the first time, our floor value of by comparing the present element of p of I must be contains in all in this tree set, because this will store all the value from 0 to I minus 1 when we will start at the ith position. So this value Alice all dot floor, or this value must be present at here. And how we ensure that this value is how we ensure that this there is no other smaller element than y is present at here. At the first time we will check that the floor value of this value is present in the Alice list or not, because we will place only those elements at here in which position Alice will 100% will the game. If this floor position is another winning position, then we do not give this position to the pop. So we will check two state at here. At the first state we will check that the present value is present, that value p of the floor value of p of I is present in the Alice list or not. So we need to find the Alice dot floor. If no element is present in the Alice, so we can directly put it at here. So this is our first point, we can put it at here. Or if obviously this condition have to be satisfied, otherwise which condition we need to satisfy at here? We need to satisfy at here that by comparing with this present position Alice dot floor, Alice will take this position as a winning strategy or winning position at the previous time or not. So Alice dot p of I Alice dot floor p of I. This will compare the minimum number of value by comparing with the p of I is present in the Alice list or not, because we will start our counting or our iteration from left to right. So by comparing with the left winning strategy, we need to compare with the Alice next smallest element or next smaller element that is present in the Alice list, or the next winning strategy from the left region. Next winning strategy from the left region. This is present in the present or not in the Alice list. If this is not present in the Alice list, then we can, this element is fit to use at here. So 1. So there is no value 1 is present at here. There is no element that is smaller than 1 at here. So just skip it. 4. When we have 4, then the smaller value of 4 in his left region is 1, and our Alice does not get any winning position between this ith position from 0 to I, between this position from 0 to I. So we can use 4 at here. And also 4 from our all sequence. If we use 3 at here, then what is the smallest value in the left region than 3? This is 1. 1 is present at here. 1 is present at here. How we will ensure that this value is no other smaller element than this is present at here? Check in the Alice list, because Alice list will pick the winning strategy or winning position at here. So if we compare 3 with the 4, there is no value. Alice value is null, or Alice floor value is null. Alice value is not present at here. Alice floor value is not present at here. So can place 3 at here. So what is the size of this built data structure? 2. So we need to use total 2 number. We get total 2 number of lucky points. This is our solving approach. So let's jump to the code. At the first time, add the leftmost element in all permutation or all tree set. Then start iteration from the second element. Try to find the smallest element from left, all, and the smallest element from left of Alice. And if smallest element from left not is equal to null, that means no, this is the leftmost position, or there is no smaller value than present element p of I is present in the left region, and the floor value or the smallest value in the list present, the smallest value in the list is present in the all. That means the smallest value in the list that is present in the all, or the smallest position, the smaller element by comparing with the I, j is present in the left region. J is present in the left region. Then go at the second step and check that the this smallest value is not present in the list. This smallest element is not present in the list. That means there is no smaller element than present element p of I is present as the winning strategy from the left or in the Alice storage. Or we need to find that if some position is stored or some position is present, then we need to find that that position is contains in the Alice list or not. That position contains in the Alice position or not. That position is contains in the Alice list or not, or the leftmost winning points or not in the leftmost winning position or not. If this will satisfy this condition, we will add into the Alice storage, and finally add all of the storage p of I in the all tree data set. At the final time, we will print the Alice size or length of the Alice storage as our answer. So this is our discussion of the latest discussion about the latest educational Codeforces round. So I think all of you can understand. So be happy, keep coding.